Hey everyone, welcome back, and today let's solve LeetCode problem 75 titled Sort Colors. So we're given an array nums with n objects colored red, white, or blue, and we need to sort them in place so that objects of the same color are adjacent with the color in the order red, white, and blue. So we'll use the integers 0, 1, and 2 to represent the color red, white, and blue respectively. And we have to solve this problem without using the library's sort function, which is pretty self-explanatory because as you can see, if I were to just do nums.sort, obviously this isn't allowed, but if I were to submit this, this would be accepted and this would be considered a valid solution. But obviously, that's not what we're going for here. Although effectively we are just supposed to sort the array in place, there is a better way to do this that obviously your interviewer is going to allow you to do, right? So before we actually get into that way, let's just go ahead and look at the examples. So in example 1, we have the input array nums to be 2, 0, 2, 1, 1, 0, and we obviously get the sorted version in ascending order of that input array of 0, 0, 1, 1, 2, 2. The red balls come first, then the white balls, and finally the blue balls, or the 0, 1, and 2 elements, respectively. And finally, in example 2, we have nums to be an input array of 2, 0, 1, and we'd output 0, 1, 2, because that is the ascending form of 2, 0, and 1. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so the way we're going to efficiently solve this problem is use counting sort. But before we actually start solving it using counting sort, let's just first discuss what actually is counting sort because it's not too common of a sorting algorithm like quicksort or merge sort, right? So counting sort is basically a non-comparison based sorting algorithm that's used when the range of input values is actually small. So instead of comparing elements like quicksort or merge sort, counting sort counts the occurrences of each unique value in the input array and uses these counts to place the element in sorted ascending or respective order. So the reason why counting sort is efficient for LeetCode for this problem is because the input really contains only 3 unique values. That's going to be 0, 1, and 2. And that's why counting sort is going to be very suitable. It performs all these operations in linear time because counting the occurrences of these 3 distinct values is going to be big O of n. It's going to be a one-pass solution. And actually reconstructing the sorted array from the counts or the occurrences of each distinct value is also going to be a big O of n or linear time solution. Okay, so with that out of the way, let's just go ahead and dive straight into the code here. So since we know that we're only going to have 3 possible distinct values in our input array nums, I'm going to set a count or a frequency of each distinct value to be initialized to an empty array of 0, 0, 0, right? Where again, it's going to store the counts or frequencies of 0, 1s, and 2s in the input array nums. And quite self-explanatorily, nums at 0 is going to store the number of zeros, nums at 1 is going to store the number of 1s or blues, whites, and nums at 2 is going to store the number of 2s or blues, right? So red, white, and blue, or 0, 1, and 2. And the indice values or index values tell you exactly that. Okay, so once we do that, now let's just regularly iterate through the input array nums. So for count in nums, we want to increment, for count, I'll just say for I, never mind. For I nums, I want to increment count at I as our iterator by 1. The reason why is because we actually want to increment the number of frequency of every single element we see by 1. For example, if we see a 2, we want to increment count at 2 by 1, indicating that we've seen 1 more 2 or 1 more blue ball in our input array nums, right? Every time we see a specific element in the range of 0 and 1 and 2, we want to increment its frequency or occurrence in the count array by 1 because we've seen it 1 more time in this iteration of our input array nums. And we'll keep doing this as we iterate through every single element in the input array and update its occurrence in our count array. So once we do that, now we'll actually do something called unpacking in Python, where we set the number of red balls, the number of white balls, and the number of blue balls equal just a count. And if you guys aren't familiar with Python, it's a little bit weird and confusing at first. It's simply, since we know that count is going to have 3 distinct elements or have a length of 3, R, W, and B are going to be set to the 3 distinct values respectively, where R is going to be mapped to the first element, W with the second element, and blue with the third element. And that works out great because R, or the 0th index, is going to tell us how many red balls there are. And W is going to tell us how many white balls there are, count at index 1. And B is going to tell us how many blue balls there are, count at index 2, when we actually populate it in the for loop at line 7 and 8. Okay? So once we do that, now we're going to use some list slicing in Python. This is the really nice part here. So we'll set nums up until index R from the beginning index equal to that number of zeros. Of course, then we're going to multiply that by R because we have R zeros, right? Where again, if per se R was 3, we'd update nums up until the 3rd index, or the very first 3 indices or values, to be 0, 0, 0. And basically it fills the first R elements with nums of 0, right? So nums up until that last index R minus 1 is going to be that number of zeros. The number of zeros times R, which is the number of red balls we actually have, which again is the number of zeros we have. And we'll use similar logic for the white and blue balls as well. We'll set nums, but in this case, with the way we're going to slice is we're going to start at index R, and we're going to go up until index R plus W, right? That's going to shift us W balls, or ones, to the right of the array. And that's going to be a 1, because that's what W is signified to be, times W, the number of W balls we have, or the number of balls, white balls we have, where this is going to fill the next W elements with ones starting from index R up till R plus W, because R plus W is going to tell us the very last index of the last white ball, okay? Or I guess R plus W minus 1. And finally, nums from R plus W index up until the end of the index input array nums is going to be 2 times the number of blue balls, which is going to be signified by B, where this is going to fill the remaining elements with 2s up until the end of the input array nums, because that's going to tell us how many blue balls we have, as that's going to be the value of B. And ultimately, after this, we can simply return nums, and the reason why is because this is going to be the final sorted array, as the zeros are going to come first, and that's going to be signified by how many R's there are, or the number of red balls, and then the white balls, or the ones, are going to come next, the number of white balls we have. And finally, at the end of the array, after we cover the beginning and middle portions, we're going to have the number of blue balls, which is going to be an array of 2 times the number of blue balls we have from R plus W up until that last index. And ultimately, we can just return nums as it would be in its sorted I don't know how to say it, sorted state, right? So if I were to submit this right now, this would actually be accepted. And it is pretty efficient. So again, for the time complexity and the space complexity, this is going to be big O of n, where n is the length of the input array, because counting the occurrences is going to take big O of n, and updating the original array is also going to take big O of n. So theoretically, I guess you could call this big O of 2 times n, but coefficients don't really matter, as you guys know, in time and space complexity. So this is really just big O of n, or a linear time solution. And for the space complexity, this is going to be big O of 1, or constant time, since the count list is always going to have a size of 3, regardless of the input size. That's the important part. Even though the length of our input array nums could be like 1,000,000, obviously that probably isn't in the constraints, yeah, it isn't, but even then, we know that our count is going to have a constant fixed size of at most 3, because we only have at most 3 distinct values for every input in every single test case in this problem, and that's why the solution is so elegant and so efficient. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.